I'm Dr. Joshua Reichert, and this is the introductory lesson for Statistics as a Language from Omega Graduate School. The essential elements for this lesson include defining statistics as a language, types of data and variables, introduction to hypotheses, populations and samples, measures of central tendency, standard deviation, and normal and non-normal distributions. I'd like to start off this lesson by encouraging you not to be afraid of statistics. At OGS, we teach you how to apply statistics for the purpose of social research, which we believe can change the world. You see, in the modern world, statistics are calculated using computer programs. You don't have to do all of the complicated math that you once had to do by hand. Really, the focus is on how to use those statistics to test research questions and hypotheses and then communicate results. Don't worry about all of the complicated math behind them. Just like research writing, we want you to know you can do it. At OGS, we have a tradition of referring to statistics as a language, and we do that because statistics are the language of research. We need statistics in social research because they're the prevailing language of science. So in medical science, for example, or physics, or space science and astronomy, chemistry, all of those sciences use statistics to make inferences about the physical world. And in social science, we're using the same approach to make inferences about how people interact and behave. The reality is the outside world is more likely to listen to numbers than words. And so we use statistics to communicate the results of social research so that we can impact the culture with our findings. And ultimately, we believe that's how we can make an impact for positive social change from the research process that we teach you here at OGS. Ultimately, it's the scientific method, that's hypothesis testing, that the world wants to hear about. And that depends on numerical values in order for it to work. At OGS, we will support both quantitative and qualitative research designs, but of course, because we're talking about statistics, we're going to be focusing on the quantitative aspect of research. So qualitative distinctions when conducting research ask things like, is this good or bad? Is this right or wrong? Is this a lot or a little? But quantitative, that is quantifying something in society, depends on numbers. So 5 1/7 versus 4 1/4, or 25% versus 50%, or 1 hour versus 24 hours. These are numerical distinctions. Qualitative distinctions tend to be more values-based and subjective, whereas quantitative distinctions tend to be more objective. We often use the word empirical to refer to quantitative research. Statistics help us understand patterns in data. We need statistics to tell us something about the world in measurable terms, and that's why it needs to be quantified or numerical. In social science, we use statistics to identify patterns in people's behavior, attitudes, knowledge, and beliefs. And statistics help us infer things about a population from a sample, and we'll be talking about that in just a moment. Populations and samples. Samples represent populations. A population is all the people in the United States, but a sample of that population is maybe 10 people from each state representing that overall population of the United States. A population is all employees in a large corporation. A sample is maybe 2 employees from each department in that corporation. And the hope is that each sample represents the population as a whole. Statistics help us understand patterns in data. Ultimately, statistics is the practice of using information from a sample, it's a smaller representative group, to gain insights about a population as a whole. And we have to do this in social research because gathering information on a population can be time-consuming, and gathering information on a population might even be impossible. So for example, if we wanted to say something about maybe all of the males over the age of 50 in a particular state or a particular small country or province, it would be virtually impossible to make contact with every single one of those people and gather the information that we need. So instead, we sample from among that population and make inferences about the population from that representative sample. Sampling from a population. So as you can imagine, a sample must be representative of that population, meaning if I'm going to choose a number of people out of a particular larger population group, I have to make sure that that sample actually represents that group. So in the last example, if I were to choose males over the age of 50, I could not include in my sample males under the age of 50 or females over the age of 50. I need to make sure that my sample actually represents the population I'm trying to find out information about. And a sample is ideally randomly selected, and that's to reduce bias. So the idea is that we don't want to just pick people we want for participation in our research. We want to have a random representation so that we know that the people who participate in our research actually represent the wider population. With that said, often in the social sciences, we use samples of convenience, and samples of convenience simply mean we may not have the ability to conduct a full random sampling, and so we sample according to whatever groups or limited participants are available to us. And that's often okay in social research as long as we clearly disclose it. True random sampling usually only occurs when we conduct what's called experimental research, which is analogous to the kind of research that's done in medical testing, pharmaceutical testing, and things like that. But it's actually quite rare in social research. And so if there needs to be a sample of convenience, that is possible, especially for dissertation research. So when using statistics, we ascribe numerical values to things in the real world which might not otherwise be represented by numbers. So we can assign numbers to people's attitudes, their knowledge, their behaviors, their belief. And we do this in order to quantify features of social interaction. And most often in social science research, this comes in the form of a survey where people provide ratings to particular questions about their attitude, knowledge, beliefs, and behaviors. Examples of quantifying social issues. So we might want to look at ratings, and this is most common in surveys. So something like rate your feelings on a scale from 1 to 5. This is, by the way, often called a Likert scale. And that may range from strongly disagree to agree to strongly agree. We might use categories, so maybe choosing one of 3 ideas from a list. I'm enthusiastic, I'm indifferent, I'm anxious. There might not be a scale, but we ask them to choose a category. And we also might look at counts. So maybe the frequency of a particular behavior, maybe how often a person walks into a room wearing a red shirt over a period of time, and that's a yes or a no. Yes, they have a red shirt, no, they don't. Or maybe which color of shirt they were wearing. So how many blue shirts, how many purple shirts, how many green shirts. And that actually says something about people's patterns of behavior. To help you wrap your mind around this, I'll share an instrument that I've used from my own personal research. In fact, you can Google my name on Google Scholar and find some of the articles that I've written using this particular instrument. This is called the DUREL, the Duke University Religion Index. And it's a very short, it's actually 5 items long, survey which tests religiosity. And it actually yields 3 variables that you can use to measure religiosity of participants. It's a validated instrument, and it's been used in psychiatric research and hospital settings, and it's quite useful for applying to many different situations and contexts. So let's look, for example, at these questions. In my life, I experienced the presence of the divine, that is God. And there are 5 ratings: definitely not true, tends not to be true, unsure, tends to be true, or definitely true of me. And you can see the rest of the questions here on this slide. So what the DUREL does is it takes those questions and ends up calculating 3 variables that can be used for measurement. So in this example, from the DUREL, we can get scores for a sample, that is the participants who completed the survey, and calculate scores for the following variables: organizational religiosity, non-organizational religiosity, and intrinsic religiosity. So for the DUREL, organizational religiosity is just church attendance, Non-organizational religiosity is private prayer and Bible study, and intrinsic religiosity is how you apply your religion or your faith to your everyday life. So once we have those scores from the sample, we can compare the scores of groups based on independent variables, which we'll talk about in a minute, such as sex, race, church affiliation, to see if there's a difference in the average scores across those groups. So for example, I might want to say, is there a statistically significant difference between males and females for organizational religiosity? Or is there a significant difference between two denominational groups for intrinsic religiosity? I might want to see if there's a correlation between organizational and non-organizational religiosity for a particular denominational group. And so with this short, validated, 5-item instrument, I can find out all kinds of information from a particular sample. And this is social research. And this is the kind of research that has the potential to change the world. Of course, the first step to conducting statistical analysis is to gather data and enter them into a spreadsheet such as Microsoft Excel or Google Sheets. A spreadsheet is organized into columns and rows. Columns run vertical and rows run horizontal. Oftentimes, we will store the questions, categories, or the independent variables and dependent variables into the columns, and we will store each record or each participant score into rows. We refer to these as observations in the social sciences, and in fact, the Winks statistical program refers to them as observations as well. When we begin thinking about the kinds of data we want to collect in social science research, we can describe these in terms of levels of data measurement, and we use the acrostic NOIR, N-O-I-R, to represent those levels of data. They are nominal, ordinal, interval, and ratio. Nominal data are numbers and categories such as type of car, sedan, SUV, truck, etc., or type of school, public, private, or charter. These are often frequency counts, so how many people drive a sedan, how many people drive an SUV, how many students are in public school, how many students are in private school, etc. Ordinal data are rankings by number where order matters, but not necessarily the difference in magnitude. So for example, if I asked you to rank your favorite sports teams from 1 to 5, it doesn't really tell me how much more you like Team 1 than you like Team 2, only that Team 1 ranks higher than Team 2. And the same may be true for ranking student test scores. So I may know that a particular student was first in the class, but I don't know by how much or how much difference separates the first ranking student from the second ranking student. So the first ranking student could have scored 100% on the test, and the next ranking student could have scored 80, and everyone else could have scored below that. All I know is that that student is ranked number 1 and the other student is ranked number 2. Interval data are numbers with consistent units between the values, where higher and lower orders are meaningful. So temperature and time are really good examples of interval data. And oftentimes in interval data, negative numbers do have meaning. So these are often called continuous data. So with temperature, we can either have a positive temperature or we can go to a negative temperature, and really that scale is conceivably infinite in either direction. We can also think about time this way. So the clock just keeps moving around and around, and there's no real zero. Whereas ratio data do have a true zero, and they can often be represented as a percentage. So there is a true zero for age. That's before you are born until your present age. There's a true zero for weight. There are true zeros for sales figures. Either you had sales or you didn't, and then you could have hundreds of thousands or millions of dollars of sales, or you could have 0 sales, and you could have 0 children or 5 children, for example. And each of these levels of measurement are appropriate under different circumstances in social science research. One is not necessarily better than the other, though interval and ratio data do tend to yield more scientifically accepted results in the long run. As we begin designing our research for data collection, we must think about independent and dependent variables. Independent variables are things about each participant which is fixed, such as demographic details, their sex, their age, their race, their zip code, or the groups they belong to, maybe their denominational affiliation, their department within a company, their school district, etc. Order and rank doesn't matter for independent variables. Numbers are often just used for categorization. They are not the thing we're trying to measure. Whereas dependent variables are the responses you collect from each participant. For example, the ratings on a survey scale for each question, attendance rates, behavior counts. Dependent variables are the thing we're actually trying to measure. So in the example of the Durrell, the independent variables may have been sex, race, denomination, maybe even a particular church, whereas the dependent variables were organizational, non-organizational, and intrinsic religiosity. Those were the things we were actually trying to measure. Using independent and dependent variables. We ask research questions about dependent variables and create groups or categories on independent variables. Our hypotheses will be about differences, similarities, probability, or correlation of dependent variables grouped around independent variables. So is there a difference between male and female? Is there a difference between racial categories? Is there a difference between denominational affiliation? Is there a difference between geographic location around the dependent variables that we're trying to measure? Let's look at some examples. These statements would loosely represent alternate hypotheses in formal research. We would actually test against null hypotheses, which we'll talk about later. But for purposes of these examples, let's review these statements. The green text represents a dependent variable, and the red text represents independent variables. For example, religiosity scores are statistically significantly different between males and females from the sample. The religiosity scores are the dependent variable, and males and females are the independent variables. There is a statistically significant correlation between intrinsic and extrinsic religiosity for African Americans from the sample. In this case, African Americans are the independent variable, the racial category, and intrinsic and extrinsic religiosity are the dependent variables. The number of employees wearing blue ties to work is predictable with 95% accuracy based on the sample. In this case, the number of employees is the dependent variable, and the category is wearing blue ties to work. So that's what we're pivoting the data on, and then we want to know how many employees wore blue ties to work and make a prediction on that basis. In statistics, there are three measures of central tendency upon which all of the rest of statistics are built. And these are the mean, median, and mode for any particular data set. The mean is the average of all the numbers in a column of data. For example, the average score of all students on a test is the mean. In this case, a data set of 2, 3, 9, and 12, 6.5 is the mean because that's the average of those numbers. So the mean is just the average. The median is the center of the data when all data points are sorted in order. It's simply the middle row of a data set for a particular column. So for example, the median of 2, 5, 7, 9, and 9 is 7 because it is in the middle of that data set. And the mode is the most frequent value represented in a particular column or particular data set. So for example, among 4, 4, 3, 4, 7, the mode is 4 because 4 is the most represented data point. In the language of social research, the mean is represented as an X with a bar above it. Oftentimes that's pronounced X bar. And you'll see that in statistics books and in the Wink software, and you'll actually use it in your own dissertation when you're reporting on data. The Greek symbol mu is also used for the population mean, but very rarely may we use that in dissertation research. Most often we're dealing with the sample mean, which is represented by the symbol X bar. Once we've collected our data and we've loaded it into a spreadsheet format, the next thing we want to know is how our data are distributed. Statisticians use the term distribution to refer to how data will look if they're graphed on what's called a histogram. And so in this example, you can see a histogram graph where the y-axis represents the frequency or the number of people who have a particular salary, and the x-axis going horizontally shows the particular monthly salary for each group of people. So in this example, it looks like about 25 people make just over $800 a month, and very, very few people make $1,500 a month. Looks like the most of the group is making just over $900 a month, and that looks like about 155, 160. So if you look at this histogram, we can look at the height of each bar to see how many people are making a particular salary per month. This is called a distribution. So I want to know how many data points I have in each particular value represented across the horizontal or x-axis. So it gives me a visual representation of what my data look like or how my data are distributed. That histogram can then be translated into what's called the normal curve. When lots of data are graphed across a horizontal axis, we usually get what's called a normal or bell curve. This means that the data are distributed evenly, so there are very few on the extremes and most of the data are in the center. That is, most of the data are close to the value of the mean or the average. So the mean or average is in the center. And when data are positive and negative, so negative going to the left, positive going to the right, the mean is often 0 or close to 0 in a normal distribution. So if you think about it, very few data are on the extreme negative, very few data are on the extreme positive, and as you move closer and closer to the average, you get more and more and more data which are closer and closer and closer to the average of the overall data set. In a normal distribution, we often want to calculate what's called the standard deviation. The standard deviation is how far data tend away from the mean in either direction. So in a normal distribution, standard deviation is symmetric about its mean. So in this example, the mean is at 0, and one standard deviation is represented to the left, and one standard deviation is represented to the right, which means there's generally an equal number of data points that are less than the mean and an equal number of data points that are greater than the mean. Then we move further to the left, and two standard deviations. We have about the same number of data points, which are 2 standard deviations away from the mean, as we do that are 2 standard deviations positive from the mean, and so on and so forth. So in this particular case, the mean is at 0, and we can see 1 standard deviation to the left, negative, 1 standard deviation to the right, positive, 2 standard deviations to the left, negative, 2 standard deviations to the right, positive, 3 standard deviations to the left, negative, 3 standard deviations to the right, positive. And the important point is that those standard deviations are symmetric or equal about the mean. And you can see the width of those columns is relatively equidistant from the mean itself. In statistics, the standard deviation is represented by the small Greek letter sigma for the population standard deviation, and then just S for the sample standard deviation. And much like the mean, we'll be working primarily with the sample standard deviation in dissertation research. You might be asking, why do we need these measures? Well, mean and standard deviation are 2 of the most important measures in statistics. They tell us a lot about a sample of data. They answer questions like, what are the average values of the data? What's the mean? How are the data distributed? How much do the values deviate from that average? That's the standard deviation. And also, are the data skewed in one particular direction or another? Standard deviation also tells us something about probability. Probability is like rolling die. It tells us how likely an event is to occur. And we can make predictions based on how probable or how improbable something might be for occurring. So using standard deviations, the area under a curve represents a probability that new data will fall into that range for a normally distributed sample. So for example, if we're looking at one standard deviation from the mean, there is a 0.68 or 68% likelihood that any new data we introduce is going to fall within that range. If we move out to 2 standard deviations from the mean, now we're covering a much wider range of that graph. We have a pretty good chance. It's 95% probability that any new data we introduce, so 95 out of 100 new data points, will fall into that range. But if we move out to the extremes and include those as well, now we have a 99% accuracy, almost 100% probability that any new data we introduce to the data set is going to fall within that range. And that's assuming that our data are normally distributed, but it does give us the ability to predict with some level of accuracy where data are going to fall based on standard deviations. Another helpful measure is the z-score. And the z-score tells us how many standard deviations away from the mean a particular data point falls. So in this example, there's a little red dot on the curve, and that's a new data point that we're looking at, and we can compute using the z-score that that particular data point is negative 1.24 standard deviations away from the mean. And that can be very helpful to let us know where that data point falls in terms of the overall distribution of data. Although the normal curve is really helpful for us understanding these broad concepts, we cannot assume normality for every data set. In fact, very few data sets in social science are normally distributed, unless they're very large samples, often 200 or more records of data, and many times it's more than that. And that's typically more than is used in a dissertation. And so most OGS students will not have more than 200 or possibly 500 or 1,000 data records in their sample. We can't assume that data are normally distributed, but we do have statistical tests for normality that we can run to tell us whether or not they are. And when we get to statistical tests, we'll see why that's very important. And we have ways to work with data which are not normally distributed. So in statistics, and we will discuss this later on, there are 2 types of procedures that we can use. Parametric procedures, which are statistical tests for normally distributed data, and non-parametric procedures, which are statistical tests for non-normally distributed data. And we need to know when to use which kind of test. And by and large, there are non-parametric procedures for every parametric procedure. So there are ways around having data which are non-normally distributed. And usually OGS students are working with non-parametric procedures. However, what we end up with in non-normal distributions are skewed data. So as opposed to the bell curve, you can see how these data look when they are distributed. And they're skewed either negatively or positively about the mean. So the mean is not close to 0 in these cases. The data are shifted one way or another based on how they fall on the histogram. And because we're often using smaller sample sizes in dissertation research, we often encounter data distributions that look more like these than they do like a normally distributed curve. And so we end up using non-parametric procedures to compute our statistics. We've learned a lot in this lesson, so I want to pause and do a knowledge check with you. I'd like you to reflect on these questions. Number 1, what types of things can we measure in social science research? Number 2, how do we ascribe numbers to social phenomena? Number 3, what is the difference between independent and dependent variables? Number 4, what are the most important measures in statistics? And number 5, why do normal versus non-normal distributions matter, and what do they tell us about data? Reflect on these questions, and I look forward to sharing more with you in the next lesson.